Okay, we'll go ahead and get started. Again, sorry for the delay. I wanted to go over with y'all today lesson 16, and it is something called integration by parts. And you use integration by parts if you cannot use like any other integration technique, like a handy formula, uh, undoing the power rule, or even use substitution won't work. So this is where integration by parts comes in. Integration by parts. Um, Let me do one last sound check and visual check. Can you hear me okay, and can you see the screen okay?
Yes, sir.
Okay, awesome. Integration by parts actually has its own specific formula. So let me maximize the whiteboard and write down the formula. If you have a given problem in the form u times dv, that's just your given integral, whatever it may be, to break it down and integrate it by parts, this is the formula: u times v minus the integral of v du. Now, how you find u and du is the same as finding the u and the du for regular u substitution. So that part hasn't changed. In order to identify and find dv and v, you have to integrate. So you'll label whatever dv may be, and then to find v, you just integrate whatever you identify dv as. So this is integration, called integration by parts, and you use this when your conventional integration techniques will not work. Now, if you pick the wrong thing to label as u or dv, if you see the problem is getting much, much worse, then no problem. Start over and just pick some new labels for u and dv. Let's start out with this basic problem. We want to integrate x times natural log of x dx. Oh, by the way, there is a bonus assignment now in my math lab. It's at the top of the assignments page. And the due date, I posted an announcement in Blackboard regarding the due date and the point value for each question.
I did see that announcement, Mr. Arnold.
Okay. You know what? I did not post an announcement in about the changing the due dates. I think I just did it. But I will go back later and double check and definitely post an announcement about the change in date. Now we have to figure out what is going to be our u and what is going to be our dv to integrate. Well, I don't want dv to be natural log of x because we don't know the integral of natural log of x without looking it up. So let u equal to natural log of x because we know the derivative of it. and let dv equal to x dx. And we can integrate that pretty easily. All right, so the derivative of natural log of x is just 1 over x dx. And the integral of x, remember you have to integrate dv in order to find v. We just do the power rule in reverse for that. So that would be 1/2 times x squared. Now let's plug everything into our integration by parts formula. So our formula is u times v minus the integral of v du. U is natural log of x, and our v is 1/2 x squared. Or we can go ahead and swap those around, write it properly. Minus the integral of v du. So that would be minus the integral of 1/2 x squared times du, which was 1 over x dx.
Mr. Arnold, before you rewrote that first part, that is natural log of x times half x squared and not minus.
Yes.
Okay.
Am I right here?
Yeah, that's a times. Okay.
Oh,
It looked like a minus.
sorry about that. It is a multiplication symbol. Now, before we integrate, you can simplify the x's. So x squared divided by x is just x. And another thing we can do before we integrate is pull out the 1/2. With some problems, you may have to use integration by parts more than once, but here we don't have to because we can find the integral of x pretty easily. So the integral of x is x squared over 2, or 1/2 times x squared. So our final answer is 1/2 x squared times natural log of x minus 1/4 x squared. And because this is not a definite integral, we're not plugging in any limits of integration. You must put a plus c in your answer. Any questions about this first problem? Again, some questions you may only need to use integration by parts just one time. Others, you may have to use it twice or sometimes 3 times. If it gets to the point where you have to use parts like 3 times or more than that, then I don't mind you going online and using an integral calculator to find your answer. All right, let's look at the next problem. And let's put our parts formula back up here. I didn't mean to erase it. Okay, our next question, we have the integral of x squared times cosine of 2x dx. We cannot integrate this by conventional means, so we need to try integration by parts. I'm just going to let u equal to x squared. Because we can easily differentiate that. So du is equal to 2x dx. And I'm going to let dv equal to our cosine 2x dx. Now, this integral you can actually look up, or you can do like a substitution. When you integrate this, you actually come up with 1/2 sine of 2x for your integral. And let me show you how I got that. I did a mini substitution. Instead of U, I used the letter A for apple, as an apple. And I let A equal to 2x. So when we take the derivative of both sides, we have dA equal to 2dx. Or that's the same thing as dx equaling 1/2 dA. So what I did then is in place of 2x, I plugged in our a, and our 1/2 goes on the outside. The integral of cosine a is sine a. And the last thing I did was just back substituted a. It was originally 2x. So that's how I got v so fast. I did a side substitution. Any questions about the a substitution? All right, we have all of our components. Let's plug them into our parts formula. U is x squared. V is 1/2 sine of 2x minus the integral of V, or the integral of 1/2 sine of 2x, times du, or 2x dx. Now for the integral, let's clean that up a little bit. And also for the first part of our answer, let's just put the x squared behind the 1/2. Over here with the integral, the 2's cancel out. And that leaves us with minus integral of x times sine of 2x. Well, we can't integrate that still by conventional means, so we have to use integration by parts again. Are there any questions about using parts the first go around? All right, second go around, let's let u equal to x. Because that derivative is just dx. And for our dv, let's use sine of 2x. Now, I'll go ahead and tell you without showing you this time around, when you integrate sine of 2x dx, you'll get negative 1/2 cosine of 2x. And again, all I did was a side substitution. I just let a equal to 2x and found my integral in similar fashion as like we did over here. All right, so let's plug everything into our parts formula. Bringing down the 1/2 x squared sine of 2x from earlier. Okay, so we got uv minus the integral of v du. Now be careful, there is a minus sign in front of the integral sign here. So bring it down. And let's use brackets. So u this time around is x. V was negative 1/2 cosine of 2x minus the integral of v. And v was negative 1/2 cosine 2x. And what am I missing? Oh, du was just dx. Now, before we integrate, let's go ahead and distribute this outside negative sign. So when we do that, excuse me, we have 1/2 x squared times sine of 2x from earlier. A negative times a negative gives us a positive 1/2 x cosine 2x. And be careful here. A negative times a negative is a positive. Times a negative will give you a negative 1/2. Integral of cosine 2x. Is everyone okay so far? This is a long process.
Yeah, this is a lot of integration.
Yes, sir. That's why you have to watch your signs. And one wrong sign could throw everything off. Now, the integral of cosine 2x dx, we don't have to integrate that again because we don't have to integrate it because we integrated it earlier. So that is 1/2 sine of 2x. So our final answer, bringing everything else down, is 1/2 x squared sine of 2x plus 1/2 x times cosine 2x minus 1/4 when I multiply the 1/2 sine of 2x, and don't forget your plus c. Again, are there any questions about any part of this problem?
I have a question, but not just pertaining to the problem. Is it better to, when you write, sine, is it better to put the parentheses around what sine of is? Or
It's actually up to you.
okay, I just didn't know if that was a preferred method of writing it out or what.
I don't think my math lab will count it wrong if you leave off the parentheses.
Okay.
Our next problem, let's actually plug in some numbers. Still using integration by parts. Let me put our formula back up here. The integral going from 1/2 to 3, 4 times x times the natural log of 2x dx. We must use integration by parts because we don't know of a handy formula that would work, or none of our conventional methods will work either. Now, we don't know the integral of natural log of 2x without relying on a formula. So, but we do know the derivative. So let natural log of 2x be our u. Because we can take the derivative of that. The derivative of natural log of 2x is 1 over 2x times the derivative of 2x. The derivative of 2x is 2. And while we're at it, we can cancel out the 2's. So du is equal to 1 over x times dx. So the rest of the problem is our dv, the 4x dx part. And we can integrate that pretty handily. By reversing the power rule, you add 1 to the original exponent. Y'all be careful. Call me if y'all need anything. That was my parents walking out. I was saying bye to them, making sure they're okay. We add 1 to the original exponent, so that would be x squared over 2. And the 2 can go into 4 2 times. So v is equal to 2x squared. Now let's plug everything into our parts formula. U times v is natural log of 2x times 2x squared. But I'm going to go ahead and put the 2x squared up front. Minus the integral of v du. V is 2x squared. And du is 1 over x dx. Now, a couple of things we can do with the integral. Move the 2 to the front of the integral sign, and also simplify the x's. So what we're ready to integrate is actually just x dx. Are there any questions before we continue? Now, the integral of x is very easy. That's just x squared over 2. But we have a 2 already in front, so those 2's cancel out. So we now have 2x squared natural log of 2x minus x squared. And now we're ready to plug in our limits of integration. Starting with the 3 first, we have 2 times 3 squared times natural log of 2 times 3 minus 3 squared. And as y'all are aware, we put a minus sign in between our substitutions. And second go around, everywhere you see an x, plug in 1/2. So I'm just taking my time and plugging everything in carefully. Now time to evaluate. 3 squared is 9, times 2 is 18, natural log of 6, minus 9. Over here, the 2's cancel out, and you're left with natural log of 1, which is actually 0. So this whole entire part that I just crossed out is 0. Minus 1/4. We have the negative sign from our fundamental theorem, so our double negatives change to one positive, 1/4. Now, if for some reason my math lab left the natural log part alone, but combined the -9 and 1/4. An easy way to combine those parts together is rewrite -9 as -36/4. That way you can easily combine the numerators and keep the common denominator. Final answer, 18 natural log of 6 minus 35/4. Any questions about this problem?
No, sir.
Okay. This one wasn't too terribly bad because we only had to use integration by parts one time. But again, as I mentioned earlier in the lecture, you may have to use the parts formula more than once. All right, our next example. We have the integral of inverse cotangent. Excuse me, I'm sorry. Of in parentheses 3y dy. Now, we don't know the integral of inverse cotangent, so let's let u equal to our inverse cotangent. And there is actually a special formula for inverse cotangent, for derivative, I'm sorry. And that should be a u outside, sorry about that. The derivative of inverse cotangent of any function u is -1 over 1 plus u squared times the derivative of u. So using our derivative formula for inverse cotangent, we have -1 over 1 plus u in this case is 3y, and we're squaring the entire 3y, times the derivative of 3y. The derivative of 3y is 3 times -1 gives us -3 all over 1 plus 9y squared dy. Now, the only part that has not been assigned a letter or part of our integration formula is dy. So we'll let dv equal to dy. And when we integrate both sides, we just get v equal to y. Now let's plug everything into our parts formula. U times V, U is our inverse cotangent of 3y, and V is just y. And I'm going to write them in reverse order. So we have y times inverse cotangent of 3y minus the integral of v du. So v is y, and du is our fraction. So that would just become now negative 3y over 1 plus 9y squared dy. I'm going to erase our u and dv part so we'll have more room to work. All right, and that's dy right here, sorry. Now, before we integrate, we can move the negative 3 in front of our integral sign. And we already have a negative, understood to be negative 1 out there anyway. So that makes it a positive 3 times the integral of y over 1 plus 9y squared dy. Now, are there any questions before we integrate our fraction?
No, sir.
Okay. We can actually integrate our fraction using regular u substitution. So let u equal to 1 plus 9y squared. Therefore, du is equal to 18y dy. And we'll just divide both sides by 18 to get dy by y dy, I'm sorry, by itself. So in place of y dy, that's our 1 over 18 du. Now there's a 3 outside our integral sign, so we can simplify the 3 and the 18. 3 can go into 18 6 times. So that'll be 1 over 6 outside our integral now. The y dy, the rest of it is du. And our denominator is u. So we now have y times inverse cotangent of 3y plus 1 over 6. The integral of 1 over u du is an integral that we are familiar with, and that is natural log. So we got natural log absolute value of u. And the absolute value is there to ensure that our natural log is always positive. So natural log absolute value of u plus c. We got one more step. and that is replace u with the 1 plus 9y squared. So final answer is y times inverse cotangent of 3y plus 1 over 6 natural log. And you can drop the absolute value sign because 1 plus 9y squared is never going to be negative. Are there any questions about this problem?
Nope.
Okay. I told you earlier that if I knew that a problem required you to use integration by parts more than twice, then you can use an integral calculator to get your answer. If this happens to be a show work problem, you can just put in your work, I used an online calculator and that will suffice. So let me switch to an integral calculator for our next problem. Can you see the web browser okay?
Yes, sir.
Okay. Symbolab is a good one. It's reliable. Let me enlarge this just a bit. The integral sign and dx are already there. All you have to do is type in your problem. So our problem is 5x to the fourth power times e isn't every day. E is being raised to the negative 4x power.
Mr. Arnold, I don't know why, but I always have a hard time seeing where you put the limits of integration in that. If there were for this problem, I see that there's not, but how do you get that in there?
Okay, you see this integral sign next to the regular one?
Oh yeah, okay. You just add that onto it.
So let's say, that's a good question. Let's say the limits of integration go from 2 to 3. So you just click in each box, type in your limits of integration.
Okay, yeah, I just didn't notice that up there in the little box there, I guess. All right, I'm just not used to these calculators, I guess.
Yeah, you use that one if you're actually plugging in numbers. Sorry about that. My house phone is ringing, but I want to go ahead and show you the correct answer. Now, when you see how long the answer is, it probably took using integration by parts, maybe at least 3 times, maybe even more. So that's why I don't mind. See how long the answer is. So I don't mind y'all using.
That'll be fun to do by hand, right?
It would take up a whole page, most definitely. So if you run across one like this where you are starting to use integration by parts more than twice, I don't mind y'all using an online calculator to get your answer. And you wouldn't even have to factor out the 5, but Symbolab did for some reason, which is fine. Let's look at a question, and not all questions require you to use integration by parts. In this particular lesson, you may just have to use some algebra or use substitution. So let me show you one like you'll see in the lesson. Is the whiteboard back up for you?
Yes, sir.
Okay. All right. We have the integral going from 0 to 4 of x times the radical or square root of 4 minus x dx. Now, before you try integration by parts, see if you can do a regular use substitution. So if I let u equal to 4 minus x, then du is equal to just negative 1 dx. Or in other words, negative du is equal to dx. Okay, so we can work with that. We can plug in a dx. We can plug in our u. The only additional thing we can't plug in just yet is x. But we can go to our original u substitution and solve for x. So if we subtract 4 from both sides of our u substitution, we get u minus 4 equal to negative 1x. If we divide everything by negative 1, we get negative u plus 4 equal to x. Or if we turn this around, we get 4 minus u equal to x. I'm checking my substitutions for u. Okay, everything's fine. Now let's plug in everything, see what we come up with. We have a negative sign on the outside because our dx is negative du. Under the radical, 4 minus x is our u. And our x is 4 minus u. Now, to make it less complicated, let's distribute that negative sign times our 4 minus u. So when we do that, that becomes u minus 4 now. Any questions so far?
Nope.
Okay. Now the square root of u can be rewritten as u raised to the 1/2 power. Well, let's distribute that u to the 1/2 power times u minus 4. 1 plus a half is 3 halves. So that's u to the 3 halves power du. Minus 4 times the integral of u to the 1 half du. We don't need integration by parts. This is just regular power rule deconstructed. So for u to the 3 halves power, we'll just add 1 to the 3 halves. And we'll divide by 3 halves plus 1. So that is u to the 5 halves power over 5 halves, or just 2 over 5 times u to the 5 halves power. Do the same thing for the other integral. We add 1 to the 1 half, and we divide by 1 half plus 1. So that gives us now u to the 3 halves power all over 3 halves. Or 2/3 times u to the 3 halves. So we have 2/5 u to the 5 halves power minus, multiply that 2/3 times the 4 that's already there. That gives us -8/3 u to the 1 half. Now, before we can evaluate our integral, we need to back substitute what u originally was. And y'all remember that u was originally 4 minus x. Oh, and that should be 3 halves. I'm so sorry. Any questions before we plug in our limits of integration?
No, sir.
Okay. Let me erase this top part so we'll have more room to work. Okay, up top, first of all, we'll plug in 4. So we have 2/5 times 4 minus 4 to the 5 halves power minus 8/3 times 4 minus 4 to the 3 halves power. And actually, in both parentheses, you get 0. So this whole entire first part is nothing but 0. Minus, let's plug in 0 second time around. So we have 2 over 5 times 4 minus 0 to the 5 halves power minus 8/3 times 4 minus 0 to the 3 halves power. What it boils down to is we're trying to find 4 to the 5 halves power and 4 to the 3 halves power. 4 to the 5 halves power, when you figure that out, is actually 32. And 4 to the 3 halves power is 8. So let's bring over what we have currently. We have our minus sign. 2/5 times 32 minus 8/3 times 8. And let's go ahead and distribute that negative sign as well as multiply by 32 and 8. So we have negative 64 over 5 plus 64 over 3. My math lab wants a single fraction for an answer, so we must rewrite each fraction to its same denominator. Our common denominator is 15. I do this in my other classes when we're discussing fractions. We just find the missing multiplier. 5 can go into 15 3 times. And 3 times negative 64 is negative 192. Second fraction, 3 can go into 15 5 times. And 64 times 5 is 320. Giving us our final answer, 128 all over 15. Any questions about this particular problem?
So it's pretty interesting that the upper limit equaled 0 without 0 being in the upper limit, and 0 not equaling 0. Because usually, when the limits of integration, when one of them 0, the whole thing is 0 when you're adding the limits of integration in there.
Oh, that's a good point because that usually happens the second substitution, right?
Right. When it's 0, it's usually it comes out to be 0, but in this case it was reversed.
Yeah. Do you think that could that 4 minus x could have had something to do with it?
Oh, definitely. Especially since the upper limit was 4.
Right. If it had been 4 minus x, then we would have gotten something. Actually, I don't know. It might have come out the same. I'm not sure.
If the upper limit had been 5, it would have came out different.
That's true. There wouldn't have been an answer because 4 minus 5 will give you a negative 1, and square root of negative 1 is not real. So I don't think you would get an answer.
Oh, that's true. Yeah.
Let's see, negative 1. Yeah, it wouldn't be a real answer. Any questions about anything else?
I don't have any more.
Okay, well, let me stop recording.